Has anyone here been to any of my speeches? My God, you like punishment. Well, let me tell you, in 1964, I gave a 10-hour lecture non-stop to four... We'll start again. In 1964, I gave a 10-hour non-stop lecture to 400 scientists and many of the presses. At the end of that 10 hours, the press came up to me and said, "John, you're up one man." That I appreciated. We are thousands. We cannot come up to you. You have to come down to us. From that day, I studied this problem and I said, you're right. How the hell can anyone learn about this technology if you're talking a lot of words, nobody knows the hell you're talking about? And they fall asleep in their chairs. If anyone thinks they came here tonight to sleep, forget it. I'm not going to let you sleep. I'm going to charge you up to as high level as I am. You won't sleep tonight. You'll still be here talking. Thank you. Now, I'll take my coat off and be one of you. I got the mic on, so I'll leave the coat on. Now, with everything, whatever you do, every one of us sometimes sees something strange, something odd. Let me give you an example. A lady is sewing. She drops a needle. She looks down for it. She cannot see it. But you can. Why? The reason is she is looking down, straight down the line of sight. She's concentrating hard to see it. You are looking along the line of light. You can see it because you see the reflection. You think she must be down, not seeing it. But the whole picture is true. We all do things, and sometimes we see something that the next person cannot see. And if we put this little bit of thing we see to use, we can often improve the project we're using. Many of us have dreams, many of us have different views on subjects, because we all see different. If we all went in a field and I came back with you all and I said, now, draw what you saw, I guarantee that there'd be very few of those drawings that are exactly the same, because we all have different ideas what we like. We only put in what we like. And this is what I consider at the age of 14. Why on earth do you have a dream that's exactly the same? Twice a year, for 6 years, you have another dream oscillating between these two dreams, exactly the same number of times. There must be a reason. And that is what I looked into. Now, I don't know how many people have seen this bit of mathematics. But tonight, first, I want to do another one. John, have we got some paper and a pen? With everything you do it because you know the keys to that problem. If you know the keys, you can do anything. I want to show you one which you probably have never seen. Pen will do. Oh, this would just got down, and I'll hand it to you. You check it on your calculator. The answers are right.
Okay.
Right. Now, anyone got a birthday today? Anyone got a birthday this week? You have. Well, let's see. How old are you?
48.
You're 48. Oh, I put my glasses on. Now, the gentleman said it's 48. Why I asked for numbers? Because if I use my number, you can say you've worked it out beforehand. But by calling up somebody, he's given a number. Now, what I want you to do, if you'd like to try it, is to take the number 1, 2, 3, 4, 5, 6, 7, 8, 9, multiplied by 48, times that answer by 9. I have the answer. How long is it going to take you to get the answer? Any more? Like to give me a number? Any other number?
$525 million, he said.
Well, we could do that, but we'll keep it to 99 for quickness, because you've got to work it out. It might take you a long time. 77. 77? Right. The same number run out by 77. Right.
Take the number, multiply it times 1, 2, 3, 4, 5, 6, 7, 8, 9. Multiply that times 9. The numbers were 48 and 77.
I thought we had a 3 square or 4 square worked out to put up on the screen so you can see. We haven't. Right. While you try to work out that, I'll get on with the next one for you to watch. Right. You can see on the screen some squares. Now, the top one is 3 squared. The answer is 9 squares. That is what you are taught. You're wrong. There are 9 fields. Each of them is a value. Each square has a value to it. Each square must add up so that at the end of the row will come to the same value. Every line, every horizontal and every vertical, the 2 diagonals. Now, that is very simple, isn't it? Because it's the most fastest one we could... Is that coming out? Yes. Right. Now, that's quick. That's easy sum. Can you read it from there? This seems to... On the top, we got 9, 2, 7. The next line is 4, 6, 8, and 5, 10, 3. I think if you add it all up, you'll find that they all add up to the same value. The 3 horizontal, the 3 vertical, and the 2 diagonal.
What's that 10 doing in it? Make that up.
Right. Now, how much do you make it per line?
18.
Are you satisfied that each line is the same value?
Yes.
Right. Now, the center number 6 is in fact 1 square, the value of 1 square. That's a shell 1. Around it is another shell. That shell value will add is 6 times 8. If you add up the outer figures, you'll find that they are the same value. The center square times 4 will give you the value of the 4 corners. This square is what we call a group 1. It circulates, it spins. That is all it can do. Now you can go up, you can go to as large a value as you want. And you may say, what good is this? Well, that is where the difference lies. Every line shown there, you can take any line, and if you say that that value is the sum of the volume that you require to make the roller, then you take the highest value. Say we look at the bottom line, then you've got 10, 5, 3 in line of their values. 10 grams of the heaviest of the elements will be the center of the roller. The smallest value will be the second shell, which is an insulated material, nylon 66, a negative charge version, acting as a double bond gate. Then we put the outer shell on, the final one, which in this case will be 5 grams. When you press this, you now get your solid roller. But there is a difference in this roller than you get when you mix all these mixtures together. You are producing a pump diode. It acts as a semiconductor. It does not act any longer like a normal rod that you would have made. Now, we can design all sorts of things from this square. But unless we understand how to go about to work these squares out, there's nothing you can do. Because when you see my work demonstrated, which will have to be another time when they can give me a whole day to lecture, you'll see what looks to you like a roller. We didn't bring the pictures down, the book pictures, but that's in the book. Now, these rollers, as we call them, they rotate quite free of the surface of the plate. The plate and the roller are made of exactly the same weight. One roller will rotate on its own around the plate. Why does it do it? That's a very interesting point. If we take a rare earth as our heaviest element to be used, and that's the center core of that roller, you have got a mass of electrons that are free. Now, let's look at this in a very simple light. If every atom got 4 spare electrons, and you have millions of atoms on every head of a pin, therefore, in that amount of 10 grams, you must have millions of electrons available to move. If we allow those electrons to move to the outside shell, they would pulse. You would get big surges of electrons, that, another big surge, and that would not be very good for our bulbs. So we have to do something, and we put nylon between them. This nylon we use is a double bond. It's not a single bond type or trouble, it's a double bond. And the electrons are allowed to pass through this double bond. And thus they are accelerated to the outside skin. When they get there, the helium is pulling more electrons in, or any of the rare earths you use are pulling more electrons into the center of that material. As they're drawn through the material, they are accelerated. As they come through the gate, they've been restricted so that you've got a steady flow. When they hit the next material, the material has to open to this flow of electrons, these tunnels. The electrons arrive on the outer side many times faster and many more millions of them. You wind your coils, and they, as a magnet or these magnetic devices, slip through the coils, you get your induced force. Thus, you have your electrical circuit. Now, there are some experiments I wanted to bring. I had far too much to carry, I couldn't bring them. But they're going to remake them in the States here, so I've got them for the next meeting. We have a plate glass, roughly 3 feet long. We have a ball race in the center, which it is bonded. That, in turn, is on a stand, so the glass plate is free to rotate. On it, we put 2 ring magnets approximately 4 to 5 inches from that center. We put 2 par magnets at the end. We wind our coils. When we put a powerful magnet in line so that it pulses just behind it at the angle, that plate rotates. That plate will continue to rotate till you stop it. Therefore, a very simple thing can be done to show you can get free energy. I don't like using the word free energy, but that is what it is. Now, when we look back to this roller of this SEG, what is happening there is precisely what is happening in that demonstration. That roller has so much torque that it wants to rotate on its central axis. 2 things are happening here. The roller is suspended above the plate by the magnetic field. At the same time, there's an eddy current, which is pulling it back down. If you got this sum right, the eddy current is just a little less than the upward thrust of the magnetic field. As that roller rotates, the faster it goes, the more the eddy current rises and pulls and holds it down at that one constant level. So it is floating. Now, no matter how fast that roller goes, it cannot leave that surface, nor can it even touch the surface. The other thing, too, that is important about this is that if we just magnetize a bar, that's a rod, we would just have 2 bands of magnetic impulses. That would not move when you put it on the plate. What happens is that would just stop it going off sideways. So what I do, I chop that rod in 8 sections, equal sections. I magnetize each one precisely the same. Now, you've still got your outer band, but you've got 6 more bands in there. Now, those bands have nothing to do with keeping it on that plate, but they do produce an immense force behind the roller. That force causes that rotating on its axis to move forward. Thus, you've got lift, you've got pull back so it don't hit the top plate, and then you've got this thrust pushing it forward. When you drop one roller on the plate, it's away. People always ask me, what's the power you use to start it? It starts itself. When you put the next roller in, you think you have to place it in a precise position. You don't. You just drop it in. It will sort itself. You put the next one, and they will keep sorting themselves out. You need 12 rollers on the first plate. Why? The reason is simple, that if you don't get 12, you do not get a smooth running roller. It's jerky. So the less you have in it, you get to a point where you get about 3 rollers, 4 rollers, and you don't get much movement. So we know from experiment, you've got to have 12. That's the minimum. On the next plate, we have another plate, we put in another set of rollers. We have the 10 extra rollers added to the 12 in the next show. We go out another plate, and we again put the 12 plus 20, the 10 extra on each of those. So what you've got a simple 3-plate, solid plate device in which you've got 3 lines of rollers spinning round. Now, the rollers, regardless which way the first one go, they all go the same way. you say, how do they get the right spacing? Well, the force of each roller balances themselves out. That is why it's self-setting. Now, the other thing, too, is that is only prime mover. You put the coils on as if you're winding any other form of power unit. Therefore, this prime mover, the bit we want to develop for the next meeting in the States here, we will show the prime mover by itself. As that, you can use that in a car engine, bus, trains, anything you want, home generator, and you just put on whatever you want to get from it. The difference between this generator and a standard generator is simply this. The unit is designed to produce a given output. That means the rollers must rotate at a given speed for a certain output. Once this output is reached, we say that the machine is now nicely balanced. There you've got the cooker on. The whole machine is nicely. You look at the temperature, it is just nice. Turn on another cooker. To achieve the power now, the rollers must increase their velocity. And they do instant. Now, you've got two cookers running. The speed of the rings are moving faster. The temperature is dropping. Put on another machine, the rollers again speed up to allow this amount of power. And the temperature is coming down. You will reach a point where you reach what we call the maximum you design the motor for. When you pass this point, the temperature just simply zooms down. At this instant, that machine acts like any other generator would do in a power station. When you suddenly got something break off and go in, the machine stops. Now, it's loaded with kinetic energy. It rips itself out the floor, chucks itself through the roof. This is what this machine does, which I learned by my misfortune. And I'd like to take you back to it because when you're experimenting with things, you get things happening you don't expect. And I'd like to show you how it went. I was put into digs, and my landlady was about 85. And at 85, you would say the bones are not very good at moving about. I think you will all agree on that. But she loved watching me fiddling with wires, sticking them on the edge. She always wanted to help to solder leads on. And every time when I said, I'll connect the circuit now, and she would say, it won't do nothing, will it? No, I was wrong. It did do something. It shot to the ceiling. And I would say, that's a stupid thing. What the hell is it on the ceiling for? I have to get a step ladder and pull it down. And I think you agree with me, with a situation like this, you would think if you make it bigger and heavier, that will keep it on the table. You're wrong, and so was I. It went up to the ceiling again. And as far as I was concerned, this was a silly situation, because I was convinced that it wouldn't do that. At least it shouldn't do. So in my head, I think I have to double its weight up a bit. And I did. Was I right? No, I was wrong. It was Christmas Eve. That one, I'm afraid, had to get me a new accommodation. It went through the ceiling, out the roof, and hovered, and then shot away. I spent the next few days in the police cell for my accommodation. So you can see that sometimes when you plan something, it don't work out the way you want it. At least it didn't for me. And I think in many cases, many people try to make something, and I'm sure there are many people in this building today, and for these few days that we've been here, that have worked hard to create something that they can see. but for some reason it does something different to what they want. And I can feel sorry for them because I know what it's like. Now, for quite a few months, no more work was done because they wouldn't allow you to do that in the police station. But when I eventually did get accommodation, I looked at this problem. I couldn't find no reference in the library as to why something lifts off the top of the surface. Everything I know do. But I forgot to tell you the most funny bit. This landlady, as I told you, was 80 odd. Boy, could she jump. She nearly jumped as good as those units that went up. She never suffered with rheumatism. Now, I think she's the only woman I know of that age that never suffered with rheumatism. So if you've got rheumatism, this is one way to cure it. So, you see, I can understand people who tell me that they've got something moving and it's not doing so good. And this is why I always ask people to come. The door is open. You can come and see me, have a chat, bring your problem, let's look at it and see if we can solve the problem. Now, you may say, how on earth did you stop that doing it? Well, I didn't really know how to do it. But it was an accident. I made a unit up, and I had it really bolted on the desk, and I wanted to solder a lead on it. I heated the iron. It was certainly pretty hot. I went to solder, and it wouldn't. The solder iron was cold. I put it back in the stand and went and got another one out. Plugged that in, got hot, and it wouldn't heat, it wouldn't melt the solder, and that was cold. And when I put it back, it heated, put it back, and then I began to get the picture. What was happening here, there were more electrons going into that iron than was being emitted by the iron. And therefore, it was cooling the system down. So I thought to myself, we can see on the thermometer that the temperature goes down as you take more power out. So what is happening, the more power you draw, it draws more power in. In fact, it starts drawing more power in than you're taking out of it. Thus, the temperature goes down. The next problem is, why? If this is the case, why does it go up in the air? And the answer we now know very well from laboratory research, that it goes superconductor. The temperature drops to 4 Kelvin. And this is why the thing completely switch over. And then that kinetic energy just forces it up into the air. So, don't do like me and have to hunt for another house. Don't think you can put weight on to keep it down. It doesn't work that way. The next thing we want to look at is how, if something wants to live, how do you put a body on it and use it? Here is where I look at the squares again. And what it simply says, that as we expand and expand these squares, we end up with an acute triangle. And if you put 4 acute triangles together, you form a disc shape. And that is how we put the body on this unusual device. We fed the power out at the rim. We switched power to the top and bottom, so we could have pressure on the top, pressure on the bottom. Now, for the first time, we were able to hold it for a while at very low running speed. So I thought, as no doubt anyone else would, that I could take it outside and let it go full speed and we would be able to hold it. I was wrong. It doesn't work like that. It goes up, and if you do this experiment, I hope you've got friendly neighbours. I found out I haven't. It goes up, clear the rooftops, and then it hovers. If your friend's got pigeons, don't do it. Because I discovered that people got pigeons get very angry. It does hover, and as it hovers, it starts getting brighter and brighter at the rim. And the interesting thing is, a lot of people tell me this is ionization of the air. they're wrong, as we have discovered. What is happening, you're raising the potential of the electrons so high, and then you're grounding them as the roller passes the coil. You're dropping them to ground. To do so, that energy that you've just released is released as photons. What you're looking at is a magnetic field containing the photons, more and more being emitting as it's building up speed. Means that glow gets brighter and brighter. It has nothing to do with centrifugal force, which you may read in many scientific reports about this. Now, you get to a point when people's radio sets come on. They've turned them off, they don't want them on. You're turning them on, but you're not turning them on at full blast. This does not make people very happy, as I discovered. Air guns are very useful, provided it's not your backside they're shooting at. Well, he said to the police when they identified who did the shooting, that I frightened his pigeons. Now, this gentleman who paid for this work to be done, he was dying of cancer. George Haynes, when I went to the house and asked for accommodation, I went up to see him and I told him about all the things I'd done. He was so excited, and this is what he said. John, the people of this area walk with their head down. Can you make them walk with their head up? And I said, I think I can. And I did. And he enjoyed it. I never, but he did. I have never seen a dying man look so happy. I am proud I made him happy, even if I suffered for it. And when it suddenly shot away, the radios went off. And he had been hammering the floor with his walking stick. And when I went up, I was looking sad. So would you if you just lost all this money? I said, I'm afraid I've lost it. Never mind, John, never mind. Did they look up? They sure did, I said. Do another one. Do another one. Now, that's a nice man. He didn't worry about me. No, he only wants to know the people looking up. I did build another one. I made it bigger. I made it heavier because I'm sure somewhere the weight had to hold it down. I again was wrong. Again it went up. Again all the radio sets switched on, and that's terrible when houses are so closely packed. It's better in the country. The noise, it's only one radio too, but when you've got hundreds of radios going, that's no fun. And of course, other people didn't see it funny either. But George did. He enjoyed it. The people did look up. And we lost it. Next one I did, he said, build another one. Build, well, it's your money, not mine. And I built another one, bigger. This time we were reaching about 16 feet in the effort to hold it down. But this time I decided I would win. So we fit a really great heavy concrete reinforced block in the ground, pegged down, and we had this thick half-inch wire cable, and we put a 20-pound pin on the end to couple it. I said to myself, I got you this time. I was wrong. I hadn't got it. It had got me instead. Boy, that did half go. So I said, this is a stupid game. And I went up to George and I said, I'm sorry, I can't win. Never mind, George, did they look up? Yes, they looked up all right. He said, well, do another one. So we did another one. This time I brought it up to 24 feet. And this time we used an inch cable and a 40-pound pin, specially cut by a firm, who guaranteed me nothing would break it. They were wrong, and so was I. This time, before I'd done it, I painted the word Jesus Saves on it. That way, but I spelled Jesus wrong, and that way I know he would know everyone was looking up. Because here, they would say, what a stupid fool he is, he can't spell Jesus right. And this is what happened. I wasn't laughing because bullets kept coming at me, but he was enjoying it, but the rest of the people weren't. In fact, listening to them from his bedroom window, I could I was feeling quite embarrassed that I spelt Jesus wrong. But I told him I had to do this so you know that they were looking up. And he loved it. He said, build one more. And we did. But we lost that too. So I couldn't win. And he died. But he died very happy. And I'm always happy if I make somebody dying happy. Even if I was unhappy at the time. But he gave me a chance to experiment. That's a chance many people never get. And it's a shame. Because I'd like to see a centre built where every inventor can come, where all the tools are there and he can work away and he can knock holes in walls if he wants with his invention. I wouldn't care. Long as he was happy, he was having a chance to do what he could see or think he could see. And he should be encouraged. We should encourage everyone. Every one of you have the rights to have a try. That I stand for. Every one of you should be able to discuss your problems, what you see with one another, so that everyone has a chance to help. That's how we built the test, the Demo 1. Because people came together, we would sit around the table, we would say, right, now what do we want for the landing leg? All ideas came up, we draw them up, we say, right, during the week, make them. Everyone sit down and they made their different legs design. The following Sunday, we come together. We look at every idea. Then we made the one we thought best in and to full scale, and then we put it to the test. Often we are wrong in our choice. We were on the first two types of landing legs that we selected, we thought were very good, but in practice they turned out not to be quite as good as we thought. The one we turned down at the beginning was in fact the best one, which again says that you may have a good idea, you may have two, then you may pick the wrong one for the job that you want to do. We got the landing legs out right. The next thing was how to build a body, because I had lectured upon my idea of this craft. We had the machine that don't want to stand the ground, and we could put it to the use. Lots of ideas came out, and the one I put forward, 400 scientists said this: John, such a design cannot support itself, let alone fly. They were wrong. For once, I was right. It did support itself, and it was called Demo 1. Now, I think we got some photos on the slide of Demo 1. In fact, it was world famous. It went out in all the media, on television, films.